Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're continuing with our series looking at writing a ray tracer in C++ using, as far as possible, only the standard libraries. And we're also using the SDL2 library so that we can display the results in a window. So today, really what I want to do is to continue with a mini-series, if you like, on looking at procedural textures, and particularly procedural noise. This is a particularly interesting area when it comes into, computer graphics and rendering, because it's a technique that was developed and is still widely used as a way of generating patterns and textures that just look a lot more like those that you find in nature. So compared to just general sort of noise that you're used to thinking of, like the black and white speckledy images that you might see on an untuned television back in the days before digital television, for example, what we can do with procedural noise is we can create patterns and textures that, as I say, more closely resemble what you see in nature. And the kind of thing we're talking about would be something like this. So I have here, this is a marble cube, as you can see, and this is a good example of the kind of texture that we're talking about. In particular, the property to note is that over a small scale, the pattern tends to vary not very much, but over a big scale, we get much larger variations of color, if you can see that there, okay? So that's just one example. That's marble. I mean, there's all sorts of other possible patterns and textures out there that we might want to create. And over this video and the next one, what I really want to focus on is how we can create similar patterns to those in the computer. So there are two sort of main techniques that are used for this. Those are value noise and gradient noise. So we're going to look at both of those. So to this video today, we're purely going to focus on value noise and how we can use that to create some interesting looking patterns, which I hope will be of interest. One caveat to note is that I'm not going to talk about seeding algorithms and hashing algorithms that are often used in procedural textures, and these are used so you can create textures that have sort of effectively infinite size with a minimum of repetition and so on, which can be very useful, but it isn't something that I need for what I'm doing. And for me, I'll explain more about what that means a little bit later, but just to get that out of the way. And also, I'm only looking at the moment of applying these textures in 2D, though of course they can be done in 3 dimensions as well. Okay, so, well, that's the introduction. Without much further ado, I suggest we jump right into it. But just before we do, let me just say that if you like this video, please do remember to hit the like button. It really does help with the YouTube algorithm. And if you haven't yet subscribed, please consider doing so. I do try to make videos as regularly as possible. I have just had a bit of a long break, but normally I try and make them as regular as possible. So if you subscribe, you don't need to worry about missing anything. Thank you very much. Right, well, without much further ado, let's jump into it and let's look at value noise. Okay, so here we are. This is now episode 15 of our series on ray tracing in C++ and part 2 of our look at procedural textures. As I just said, focusing this time on value noise. So, as I've just said, value noise really, and indeed gradient noise, both of them are forms of procedural noise that can be used to create more natural looking patterns, often similar to those found in nature, such as the marble cube that I showed you just now. These patterns have very small variation over small distances, but much larger variation over larger distances. Okay, before we can talk about value noise itself, I just wanted to talk about bilinear interpolation. So I'm assuming that everyone is basically familiar with the idea of linear interpolation, where we've given two values. For example, say at point A and point B here, we can interpolate the value very easily anywhere in between point A and B. So bilinear interpolation simply extends that into 2 dimensions. So if we have 4 values, A, B, C, and D, representing the corners of a rectangular region, in this case it's square, it doesn't have to be, then what we want to be able to do is to interpolate the value shown at the blue dot, which could be anywhere inside this square given by the 4 corners A, B, C, and D. So let's just have a quick look at how we do that, and why this is important will hopefully become obvious. Now, the first thing that we do is we imagine a line through our point, the location where we want to interpolate the values, and we see where that line intersects the lines between the corners A and C and the corners B and D. And what we're going to do is create a new variable that we're calling t that effectively encodes our position between A and C. So we call it t underscore AC, and it varies between 0, representing a point at A, and 1, representing a point at C. And we do the same over here with t underscore BD, which goes from 0 for B to 1 at D. Okay, so we will have some arbitrary value here, TAC, that represents the vertical position, if you like, of the point whose value we want to interpolate. And we're going to label those 2 points E and F. Okay, so what we then do is we can then construct another line between E and F, and we have another value of t that would vary from 0 at E to 1 at F, and is t underscore EF, representing then the horizontal location of the point that we want to obtain the value at. And we can use linear interpolation then between the values at A and C and also the values at B and D. So this is the standard equation for linear interpolation. So we get the value at E, V underscore E, is equal to the value at A plus T underscore AC multiplied by the difference between the value at C and the value at A. That is the standard equation for linear interpolation. And we have the same over here. To get the value at F is simply the value at B plus T underscore BD multiplied by the difference between the value at D and the value at B. So that gives us the values at E and F, and then finally we simply use linear interpolation between the values at E and F to give our value V at the point that we want. So that is then simply the value at E plus T underscore EF, this one, multiplied by the value at F minus the value at E. And that's it. And just to note, for a regular grid with squares, TAC is of course always going to be equal to TBC. Okay, so that's it really for bilinear interpolation. What does that mean actually in terms of how we go about making value noise? Well, the very basic principle of value noise is that we assign a value to the corners of our square, so a separate value to A, B, C and D. We probably want to pick those values at random, and then we simply interpolate in between those. So we could consider the very simplest case where we have a single square and we simply assign values to the corners of that square, and then we interpolate between that to get our pattern. And if we do something like that, you will get something like this, as you can see in the animation here. Okay, so in this animation you can see that we arrange different values at the corners represented by these vertical arrows. The height of the arrow represents the actual number. And you can see when we interpolate between those values, we get the kind of patterns that you see going on here. Okay. Okay, now, so there's one other thing that I wanted to talk about, again, to do with linear interpolation. We have just talked about that, so this is not a repeat, though it seems like it to start with. But I just wanted to recap the very basic equation for basic linear interpolation. We know all of that. So in this case, we have a y0 is equal to the v1, and y1 is equal to v2, okay? And then we linearly interpolate between them, we would get something like that. Now the problem with that approach is what happens if we introduce a third value? And what we're doing now is interpolating between the three values. And if we just do that with linear interpolation, we interpolate between v1 and v2 using the standard equation. We interpolate between v2 and v3 using the standard equation, okay? And that gives us this kind of pattern that we would see here, with a note that it has a sharp corner here. And if we were to extend the grid on which we're computing our value noise to have more than just one square, then we would encounter this problem, because we're going to have sudden changes between the different squares, which doesn't necessarily look very good. So what we do instead is we use something called smooth step interpolation, and this is basically the same as the equation for linear interpolation, but instead of just having t multiplied by the difference between v2 and v1, we now replace t with 3t squared minus 2t cubed, okay? Everything else is the same, but now if we use that, so we use this equation to interpolate between v1 and v2 exactly as before, and we use it to interpolate between v2 and v3 as before. We do both interpolations separately, but notice how the corner between them is now smooth, okay? Hence the name smooth step. Very useful function to know, really useful technique, generally where you have any application where you need to join together multiple linear interpolations. So we will be using that, and we'll see that when we come to look at the code later. Okay, so just a quick compare, that is, as I just said, let's see them side by side, that is what the two look like. Linear interpolation, square, really angular corners. Smooth step interpolation is, as the name implies, a nice smooth rounded corner between all of our points. Right. Okay, so in the case that we have multiple squares, if we want to make our value noise more interesting, and in fact we can have as many squares as we like, depending on the level of detail that we want to achieve. So in this case, we've created a 5 by 5 grid with, of course, 25 points from V0 to V24. And the way this works is that we have some arbitrary point at which we want to compute the value, here indicated in blue. And what we simply do is we choose the 4 points that surround the point that we're interested in, and then we use our bilinear interpolation as we've just talked about. If our point was over here, for example, then we would use the values of V0, V1, V5 and V6. In the case that we just looked at, we use the values of V18, V19, V23 and V24. Okay, and that's it. So what does that look like? Well, let's look at a couple more animations. This first animation here, this shows the case where we've extended our grid. So now we have a 3 by 3 grid. As we develop the texture, as we vary these values here, again indicated by the vertical arrows, you can see how we achieve the kinds of interesting patterns that we want. And again, in this final case here, we have even more points representing even more detail, and you can see how we have a much more detailed result. Okay, so that is basically it for the theory behind value noise. What I want to do now is jump into the C++ code, have a quick look at how I've gone about implementing it. It's not necessarily the best way of doing it, or, as I say, the standard way of doing it, but it does work within the caveat that I mentioned at the beginning, that I'm not going to talk about hashing algorithms and that kind of thing. Okay, so let's jump into the C++ code and have a look at what's going on. Okay, so the first thing, just quickly at my terminal window, I'm in the QB Raytrace folder. If you've cloned the repository from GitHub, you should have this, or if you've been following along, you should at least have something very similar. If we go into the QB Raytrace directory or folder, these are the main files, and you can see what I've added a QB noise folder, okay, and I've put all of the code that we need into that. So if we go into QB noise, let's have a look at that. You see I've created the files noise base, or the class is noise base, so it's a base class for all of our noise, and val noise generator, which is a noise generator for value noise. And if we go on to create other types of noise, we can create new generator classes for those accordingly. Okay, it's really as simple as that, so not too much to talk about today. So let's go back to the root folder. Okay. So here we are. This is the noisebase.hpp file, and it's really very simple. So this is our base class, so we're declaring some of the methods as virtual. We're using the qbrt namespace as always, and we're putting this in a sub namespace called noise. I don't like doing nested namespaces too much, but I think 2 levels is not too bad. And we create our class called noisebase, and we have our public functions or public methods. We have the constructor, virtual destructor, as we've talked about before. We have a function to get the value at a specified location, so that makes sense. So we're using u and v for our texture space coordinates. If you don't know if that doesn't make sense to you, then I suggest go back and look at the previous episodes I've done on UV mapping and textures. So that's simply declared virtual. It returns a double, and it's called getValue, and it accepts as input doubles for u and v. We have our function for linear interpolation, so simply called lerp. It returns a double, accepts the 2 values and the fractional position between them, between 0 and 1. We have a function to set up the grid that accepts an input of the scale. That's the number of grid squares that we want in each dimension. And then we finally have an integer there simply to store the scale. And that's actually it. That is everything that we need for the header file for noisebase. So that is noisebase.hpp. Okay, let's have a look at noisebase.cpp. So here we are. This is noisebase.cpp. First thing we do, of course, hash include noisebase.hpp. We declare our default constructor and the constructor and the destructor. Obviously, we don't need any functions in those. And our default getValue function, this is, of course, meant to be overridden by whatever class is inheriting from this one. So we don't need to do anything. So the getValue function simply returns the default value of 0. We have our function for linear interpolation. Now this implements the smooth step fade that we've just talked about, which we can do this way: IPOS times 3 minus 2 times IPOS. If you expand that out, you'll find it goes back to the equation that we started with. Doing it this way simply has the advantage of reducing or minimizing the number of multiplications that we need to perform. I've also put in the code there for linear fade. If we want to use it, we can uncomment that instead. And then we have the actual linear interpolation is just return v1 plus fade times v2 minus v1, and that's it. And the setup grid function, the default one, simply sets the scale. And that's it. That is noisebase.cpp. Really simple. Okay, so let's have a look at the code for the value noise generator, starting with valNoiseGenerator.hpp. Okay, this is valNoiseGenerator.hpp. Okay, so we of course include some stuff that we need, and we hash include noisebase.hpp. We're in the QBRT namespace and the noise namespace, and we declare our class valNoiseGenerator that inherits from noisebase. Okay, pretty straightforward. We have our constructor, and we override the virtual destructor, of course. We need to override the getValue function that gets the value at a specific location, and we need to override the setup grid function. Okay, and we have no private functions or values at the moment, and for debug purposes I have declared these as public, but it would be proper for these to be private. So what we're going to do is simply store a grid of vectors. Now this is one way of implementing a two-dimensional array in C++. We're using the std vector class to handle this. So we create a vector of doubles. Okay, a vector of vectors of doubles, that's right, which gives us a two-dimensional grid, m_value grid. So what we're doing is we're going to use that to store the value at each of the corners of all of the squares. And this is why I mentioned the important caveat at the beginning that I'm not going to talk about hashing algorithms, because what I'm doing is I'm going to pre-initialize all of the values at the corners of the squares at the point that the noise generator class is created. Now this is not the traditional way that procedural noise is done. Normally procedural noise uses some kind of hashing algorithm or some kind of pseudo-random sequence so that it can generate the values, it can compute the values at the corners on the fly, at runtime, and that saves obviously having to store them. It means you can make the texture arbitrarily large and you don't have to worry about repeating and things like that. However, for the kind of things that I want to do, I don't have a problem with simply storing the value at each corner. Yeah, I'm not going for real time, and I'm not particularly concerned about the extra RAM it's going to use. It's not a big deal for what I'm doing. If you are doing some kind of assignment or coursework project or something that needs to look at procedural noise, do be very careful about this, because it may well be they require you to do it the traditional way and not the way I'm doing it. So do just bear that in mind. Okay, right. That is pretty much everything for the value noise generator header file, except that we have a boolean called m_wrap, which we default to false. Now that is used to indicate whether we want the texture to smoothly wrap around so that it's cyclical, or if you want it to be completely different at the edges. Okay, but that is it for valNoiseGenerator.hpp. Let's have a look at valNoiseGenerator.cpp. Okay, this is valNoiseGenerator.cpp. Okay, this is not too much to talk about here. We obviously import the HPP file we've just talked about. In our constructor function, we have a call to set up grid, which we use to set up a default grid of size 2. Okay, and we don't need anything in the destructor. Before we go to that, let's just have a look at the function to configure the grid. So this is setup grid. Here we are, setup grid. It gives us integer a scale value, okay, which we store in m_scale, and that's simply the number of squares. It's a scale of 2 would mean 2 by 2, 3, 3 by 3, and so on. We're then using the random number generator here, so we set up a random device that we call randdev, and we set up a seed sequence, okay, which that's a standard way of doing it. We just put in concatenate those values together to create a seed sequence, okay, like so. And we can either use the seed sequence or not, okay, and I've put this in the comment here. Use the seed version if you want a different pattern every time, or use without the seed or with a fixed seed if you want the pattern to remain the same every time. So that's kind of important. If you want to do animations or something, you want it to stay the same for every frame, okay, so that makes sense. So either comment out those depending on what you want. We set up our random number distribution. We want uniform real numbers between 0 and 1, so we use the std uniform real distribution class to do that. which we call random distribution, and then we're going to simply generate our grid of random vectors. So the first thing we have to do is clear m_value grid of anything that might have been stored before. We resize it to the size we want, plus 1. Okay, so m_scale plus 1, because if we want a 2 by 2 grid of squares, we have a 3 by 3 grid of corners, if you think about it. Okay, so that's important. And this simply initializes all of the initial values to 0, and we simply loop through 0 up to m scale and for x, and 0 up to m scale for y, and we store a random value at every position. Okay, as I say, in the traditional way of doing it, this would be done with some kind of hashing algorithm or pseudo-random sequence, so you don't have to pre-calculate and store the values. But anyway, if the wrap flag is true, then we have a little bit of extra code. We simply modify the values at the edges, at the far edge, arbitrarily I suppose you could say the right-hand edge to be equal to the value at the left-hand edge, and the value at the bottom to be equal to the value at the top. Okay, pretty basic if you look through that. Okay, that is the function that sets up the grid. So let's have a look. How do we actually compute the value? So we have our function here, getValue, at a particular x and y. The first thing that we need to do is to ensure that x and y are cyclic, so they vary between 0 and 1. If you put in a value greater than 1, it's going to go back to being somewhere between 0 and 1, so you get a cyclic pattern. Okay, so we do that using the floating point modulo operator. Okay, really easy. And we then convert x and y to a range of 1, just to really make absolutely sure, because these will be between -1 and 1. Okay, so that's important. X and y, or u and v, vary between -1 and 1 in the coordinate system I'm using. So we modify them to be between a range of 0 and 1 simply by adding 1 and dividing by 2. Okay. We determine the spacing of the grid boundaries, which is simply 1 over the scale. So that's really easily. You static cast the scale to a double because it's an integer. We compute the local x and y, so fmod, floating point modulo operator of x with grid spacing and y with grid spacing to get those. So those are the local x and y within the grid that we're looking at. So our point could be anywhere within the UV space, but we want to find out where it is within the particular square that we're talking about. So this simply gives us that value, so between 0 and 1 within the particular square that we're in. We then compute the corner indices, so we need to find which indices in our array of pre-calculated values are the 4 corners around that point. Okay, so we do that here. We compute min x and min y using the static cast to integer of x minus local x times scale and y minus local y times scale. And then we simply go through and we calculate these. So C1x index is the maximum of min x or 0. C1y index is equal to the maximum of min y and 0. And then we do so C2 x and y, C3 x and y, and C4 x and y, as you can see there. If you follow through those, I think you'll see what's going on. We then simply extract the 4 values, so we have v1, v2, v3, and v4, which are simply obtained from the value grid. So we do m_value grid dot at c1xi dot at c1yi, and I think you can see how that works for the rest of them. And then we simply do the bilinear interpolation. As I talked about before, we calculate x weight and y weight, which are our values between the TAC and TBD values that we saw in the first slide. We use linear interpolation from the lerp function, which is from the base class, to do that. And we do that for T1 and T2, and then we simply lerp between T1 and T2, okay, using x weight. And that's it. That's really everything that we need to do to implement value noise. It is actually really very simple. So very quickly, before we can demonstrate that, let's just have a quick look at the scene class and how I've set that up to create a scene that shows what this actually does. Before we can actually implement value noise, we need to create a texture to go with it. So in the QB textures directory, I've created a file called basicvalnoise.hpp. So this is basicvalnoise.hpp. I'm not going to talk about this in any great detail because I've covered the basic structure of my texture class and instances before. But we do have a couple of specific things here to set the color map, to set the amplitude, and to set the scale. And we store our color map. We're storing color maps using the color map class that we talked about in the previous video. So if you don't know what that is, go back and have a look at that. And we also instantiate a noise generator, and we set default values for the amplitude and the scale. That is everything for basicvalnoise.hpp. Let's have a look at basicvalnoise.cpp. Basicvalnoise.cpp, obviously in our constructor we just set up the grid for the noise generator. And then in our getColor function, I've described all of this before, really. So we apply our local transform to the UV coordinates to get new U and new V, and we then compute our local color. So if we don't have a color map, we simply output purple, because that makes no sense. If we do have a color map, we compute map position simply by calling the getValue method for noise generator, and that returns a value between 0 and 1. We use SDD clamp just to absolutely make sure that it's between 0 and 1. And then we simply pass that value to our color map to get the color corresponding to that particular position, okay, which is then the value that we return. It's as easy as that. Set color map simply stores the color map, set amplitude stores the amplitude, and set scale simply stores the scale and calls the setup grid function for the noise generator. And that's it, really. That's our basic implementation of a very simple texture that will implement the value noise that we've just been talking about. So let's have a quick look at the scene class that I've used just so we can create an image that shows what's going on. Here we are in scene.cpp. Obviously I've included the basic val noise texture that we've just talked about. Everything else here is the same as it's been. We create our texture here, so we create val noise texture using std make shared qbrt : texture : basic val noise. We create an instance of that. We set the color map to noise map, which I have defined somewhere. Yes, here. Apologies, I should have talked about that first. So we create the noise map first as a color map. There we go, and we set the stops at 0, 1/2, and 1 to those colors accordingly. Okay, so that's the red, green, and blue values of those colors. And then we create our texture. We assign the color map. We set the amplitude to 1, and we set the scale to 4. Okay, so a 4x4 grid of squares. We then create a material to go with that. Again, we've talked about that before, but we just set the base color to white. We set the reflectivity to 0.2, shininess to 32, and we assign the texture, val noise texture. And then we create our objects. We've got an image sphere, a plane, and a box, and a floor. And again, that's all exactly the same as what we've covered before. And we put those into the scene, put our lights, and we do the rendering. Okay, that's basically it for the scene class. So let's have a look. Let's compile that. Let's run it, and let's see what we get. Okay, so just at my terminal window, I am simply using gmake as I always do. So if we run make, that will run through and do the compile. I did have to modify, and you will have to do that, to modify the make file to include the new QB noise directory, but that's done in exactly the same way as we've done for all of the others. So just let that run through and compile. We shouldn't get any errors because I've tested it before. We don't. There we go. So if we run cube.slash, let's clear that, run./qbray, and we see it runs through, renders each line of our image, and hopefully, bosh, there we go. So that is the value noise that we've created. Now you can play around with the different parameters and everything else and change that however you want, but as a very basic demonstration, I thought that really wasn't too bad. And you can see that the pattern has the characteristics that we talked about at the beginning. So over a small distance, the color varies only a small amount, but over a larger distance, you get much greater variations in the color, which is beginning to represent the kind of pattern that we want. Anyway, there we go. That's really everything that I wanted to talk about today. I really hope you found that video to be interesting and useful. And like I say, it's only a very basic intro really to a much bigger topic of procedural noise. And in the next video, we're going to go on to look at gradient noise, which is quite a simple extension to the principles that we've talked about today for value noise. But it allows us to create slightly more convincing and slightly more natural looking patterns than we can with simple value noise. Okay, so anyway, listen, I really hope you've enjoyed that. If you have liked it, please do remember to hit the like button. If you haven't subscribed already, then really please do consider doing so, so that you don't have to miss any future videos. And yeah, there we go. Listen, as I say, I hope you've enjoyed it. I had a great deal of pleasure making this video, so I hope it was enjoyable for you too. And I really look forward to seeing you in the next one. Thank you very much for watching. Bye.